Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through one of the most enormous known engines in the observable universe, TON 618. For now, imagine a quiet room on Earth, a dark window, and a single point of light so distant that it looks almost ordinary. Behind that small point is a quasar, and behind the quasar is a black hole so massive that ordinary scale begins to lose its grip. Hello there, and welcome to the Hypnos Sleep Channel. I'm really glad you're here. Maybe you're already lying down. Maybe you're sitting somewhere quiet. Or maybe this video is playing softly while you wind down after a long day. However you've arrived, you're in the right place. The Hypnos Sleep Channel is all about exploring big ideas in a calm and gentle way. No rush, no pressure to keep up with every detail. Just a slow journey through science, curiosity, and the universe. Designed to help your mind relax while it learns something new. Tonight, we're going to explore a question that sounds simple at first. How big is TON 618 really? Now, if you've never heard of TON 618 before, that's completely okay. Even among astronomical objects, it's not something that usually comes up in everyday conversation. But once you learn about it, it quickly becomes one of those things that quietly reshapes the way you think about the universe. Because TON 618 isn't just large. It's not just extremely large. It's one of the largest black holes we have ever discovered. And when scientists try to describe its size, they often run into a strange problem. The numbers are so enormous that our brains struggle to attach any real meaning to them. We can write the numbers down. We can say them out loud. But actually, imagining what they represent is another matter entirely. That's what we're going to explore together tonight. Not quickly, not with complicated math or technical language. Instead, we'll move slowly, step by step, building a picture of just how enormous this object really is. A useful caution belongs beside any object this large. Astronomers can estimate the mass of a distant quasar's central black hole, but the estimate depends on the light we can measure, the motion of gas near the center, and the model used to connect that motion to gravity. So TON 618 is best described as one of the most massive black holes inferred from quasar observations, not as a permanently settled final record holder. But before we dive into the deep end of cosmic scale, let me ask you something simple. Maybe you're at home, somewhere quiet. Maybe the lights are already off. Perhaps you're curled up under a blanket. Or maybe this video is playing softly on a phone beside your bed. Wherever you are in the world, it's interesting to remember that while you're listening to this, the universe above you is quietly continuing its vast and complicated story. Galaxies are drifting through space. And far beyond the reach of even the most powerful telescopes you could imagine looking through with your own eyes, TON 618 sits in the distant universe doing what black holes do best, pulling, consuming, shaping the space around it. It's always nice to see how far these quiet science journeys travel around the world. All right, now that we're settled in, let's begin with a very simple thought. Most of us have a basic idea of what a black hole is. Even if you've never studied astronomy, you've probably heard the phrase before. Black holes appear in movies, documentaries, and science books all the time. They've become one of the most famous objects in the universe. Usually, they're described in a way that sounds a little mysterious. A place where gravity is so strong that nothing can escape, not even light. That description is actually quite accurate. A black hole forms when a large amount of matter is squeezed into an incredibly small region of space. When enough mass is packed together like that, gravity becomes extremely intense. If something gets too close, it can no longer escape that gravitational pull. There's a boundary around a black hole called the event horizon. Once something crosses that boundary, there's no coming back. But here's something that might surprise you. Black holes are not all the same size. In fact, they come in a wide range of sizes, from relatively small ones formed by collapsing stars to enormous monsters sitting in the centers of galaxies. For example, if a very massive star runs out of fuel and collapses at the end of its life, it can leave behind a black hole that weighs maybe 10 times the mass of our sun. That might already sound huge, and in a way it is. 10 suns worth of mass compressed into a region only a few dozen kilometers across is an astonishing thing. But compared to the giants of the universe, those stellar black holes are actually quite modest. At the center of most galaxies, including our own Milky Way, scientists have found something much larger. These are called supermassive black holes. The one at the center of our galaxy is known as Sagittarius, a star. Its mass is about 4 million times the mass of the Sun. That number alone is already difficult to picture. 4 million suns, and yet even that enormous object turns out to be relatively small compared to TON 618. The black hole itself is not the part that shines. The light comes from gas outside the horizon. That gas falls inward, rubs, heats, and glows in an accretion flow so bright that the compact central engine can outshine the galaxy around it. Because TON 618 belongs to an even more extreme category. It's what astronomers call an ultramassive black hole. And its mass is so large that when scientists first calculated it, the result seemed almost unbelievable. TON 618 is estimated to contain around 66 billion times the mass of our Sun. Just saying the number out loud feels a little strange. Our brains are very comfortable with numbers like 10 or 100 or even 1,000. But once we move into billions, the scale becomes slippery. A billion seconds, for example, is more than 30 years. A billion minutes is over 1,900. So when we say that TON 618 contains 66 billion suns worth of mass, we're stepping into a scale that stretches far beyond everyday experience. But here's where things become even more interesting. When people hear the word mass, they often imagine weight, something heavy, something dense. However, the size of a black hole is not just about how heavy it is. It's also about how wide the event horizon becomes. And for a black hole with tens of billions of solar masses, that event horizon grows to a truly enormous size. Large enough, in fact, to swallow our entire solar system many times over. We'll explore that comparison later, because it turns out to be one of the easiest ways to visualize the scale. For now, just keep one idea in mind. TON 618 is not merely a little bigger than other black holes. It's operating on an entirely different level. To understand how scientists discovered something this large, we need to step back for a moment and think about how astronomers actually study objects that are incredibly far away. After all, no one has ever visited a black hole. We can't send a spacecraft to hover nearby and take pictures. Even the closest black holes are far beyond the reach of current technology. Instead, astronomers rely on light. Telescopes collect tiny amounts of light that have traveled across the universe for millions or even billions of years. By analyzing that light carefully, scientists can learn a surprising amount about distant objects. They can measure how fast something is moving. They can estimate its temperature. They can even figure out how much mass might be present. TON 618 was discovered through this kind of careful observation. At first, it didn't appear as a black hole at all. What astronomers actually saw was something called a quasar. Quasars are among the brightest objects in the universe. They shine with incredible intensity, often outshining the entire galaxy that surrounds them. That brightness doesn't come from the black hole itself, because black holes don't emit light. Instead, it comes from the matter swirling around the black hole. Gas and dust falling toward a black hole don't drop straight in immediately. Instead, they spiral inward, forming a spinning structure called an accretion disk. As that material spirals closer and closer, it heats up dramatically. Temperatures in these disks can reach millions of degrees. At those temperatures, the gas begins to glow intensely, producing enormous amounts of radiation. That glowing disk is what astronomers see from across the universe. And in the case of TON 618, the quasar it produces is unbelievably bright. There is also an important difference between the event horizon and the black hole shadow. The horizon is the one-way boundary. The shadow is the dark region an observer may infer from light bending around the hole. Telescopes do not photograph a solid surface because there is no surface there to photograph. So bright that it can be detected from billions of light years away. When astronomers studied the light coming from this distant quasar, they noticed something unusual. The gas around it was moving extremely fast, far faster than what would normally be expected. The only way to explain those speeds was the presence of an extraordinarily massive black hole. By analyzing the motion of the gas and the brightness of the quasar, scientists were able to estimate the mass of the object at its center. That's how they arrived at the astonishing figure of around 66 billion solar masses. Even today, TON 618 remains one of the most massive black holes we know about. And that raises a very natural question. If it's so massive, how big is it physically? How wide is the region where its gravity becomes impossible to escape? In other words, what would the event horizon actually look like if we could see it? Answering that question requires us to think carefully about scale. Because space, as it turns out, is very good at making even enormous things seem small. For example, our sun feels huge when we think about it here on Earth. It's more than 100 times wider than our planet, and it contains more than 99% of the mass in the entire solar system. Yet, when astronomers compare the sun to other stars, it turns out to be fairly ordinary. And when we compare stars to black holes, the scale shifts again. TON 618 sits at the extreme end of that scale. Its event horizon stretches across a region of space so wide that if it replaced the sun at the center of our solar system, the boundary of no return would extend far beyond the orbits of many planets. But before we get into those comparisons in detail, it helps to take a moment to consider something else. Our brains are not naturally designed to understand cosmic distances. We evolved to think about things like walking distances, mountains, rivers, and maybe the size of cities. Even the scale of Earth itself can be difficult to fully appreciate. Once we start talking about objects that span billions of kilometers, or masses that exceed billions of suns, we're entering a realm where intuition becomes unreliable. That's why astronomers often rely on comparisons. They take something familiar, like our solar system, and place it next to something unfamiliar, like TON 618. By stacking those comparisons carefully, they slowly build a picture that our minds can begin to grasp. And step by step, we'll begin to answer the question that brought us here tonight. Just how big is TON 618 really? Somewhere above you right now, the night sky is quietly stretching in every direction. You might not be looking at it at this exact moment. Perhaps the curtains are closed or the lights are off and you're already resting. Maybe the sky outside is cloudy, or maybe it's glowing softly with the light of a city that never completely sleeps. But whether we see it or not, the sky is always there. A vast ceiling of space that surrounds our small planet on all sides. If you've ever stepped outside on a clear night far away from city lights, you probably remember that feeling. Jets, when they appear around active black holes, do not come from inside the black hole. They are launched by the magnetic fields and hot plasma in the environment around it, outside the horizon. In some active galaxies, these jets can draw lines through space far larger than the visible disk of a galaxy. The first thing many people notice is how many stars there are. Not just a handful scattered across the sky, but thousands of faint points of light quietly shining from enormous distances away. At first, they all look roughly the same. Tiny dots. Some brighter than others, some dimmer, but still just points of light against the darkness. And yet each one of those lights is something enormous. Most of them are stars far larger than our sun. Some belong to distant galaxies containing hundreds of billions of stars. Others are objects so energetic that they outshine entire galaxies by themselves. The strange thing about the night sky is that it hides its scale very well. Everything appears small. Everything appears calm and distant. Even the largest structures in the universe shrink down to tiny specks when we look at them from here on Earth. This creates a kind of illusion. When we glance upward, the universe doesn't look particularly large. It looks peaceful, quiet, manageable even. But that impression fades very quickly once we begin asking a simple question. How big are the things we're actually looking at? To answer that question, astronomers have had to build an entirely new way of thinking about size and distance. Because the scales involved in space are so large that ordinary units like kilometers or miles stop being very helpful. Let's start with something familiar. The distance between Earth and the Moon is about 384,000 kilometers. That already feels quite large by everyday standards. Driving that far would take several days without stopping. Flying that distance in an airplane would take many hours. Yet, in astronomical terms, the Moon is practically right next door. Light from the moon reaches Earth in just over 1 second. Now compare that to the distance between Earth and the Sun. Our planet orbits the Sun at an average distance of about 150 million kilometers. That number is so large that astronomers often shorten it into a special unit called an astronomical unit, or AU. 1 AU simply means the average distance between Earth and the Sun. Even with that enormous distance, sunlight still reaches us fairly quickly. It takes about 8 minutes for light to travel from the Sun to Earth. So far, the scale still feels somewhat understandable. The Moon is 1 second away. The Sun is 8 minutes away. But once we move beyond our solar system, the numbers begin to grow rapidly. The nearest star system to Earth is Alpha Centauri. Its light takes more than 4 years to reach us. That means the light we see from that star tonight actually left it 4 years ago. For a non-spinning black hole, the horizon radius scales almost directly with mass, roughly 3 kilometers for every solar mass. Real black holes spin, and the exact geometry is more subtle, but the simple rule is a good lantern for walking through the scale. Because of distances like this, astronomers use another unit called the light year. A light year is simply the distance light travels in 1 year. Since light moves at about 300,000 kilometers per second, it covers an enormous amount of distance in that time. 1 light year equals about 9.46 trillion. Already our minds are being pushed into unfamiliar territory. Trillions, numbers that stretch far beyond everyday experience, but the scale keeps expanding. Our entire Milky Way galaxy is about 100,000 light years across. Inside it are hundreds of billions of stars, along with clouds of gas, dust, planets, and many other strange objects. And at the center of this galaxy sits a supermassive black hole called Sagittarius, a star. Earlier, we mentioned that this black hole contains around 4 million times the mass of our Sun. That might sound enormous, and it truly is. Universe, Sagittarius. A star is actually quite modest. TON 618, the object we're slowly working our way toward tonight, is far beyond that scale. But before we return to it, let's pause and think about something interesting. When you look up at the night sky, the stars appear scattered across a flat surface, almost like small lights on a dark ceiling. Your eyes can't easily detect how far away they really are. Some stars that appear close together in the sky are actually separated by hundreds or thousands of light years in space. Others may appear faint, not because they are small, but because they are unimaginably far. This is one of the reasons astronomy is such a patient science. Understanding the true scale of the universe requires careful measurement, observation, and a willingness to rethink our assumptions. For thousands of years, humans believed that Earth was at the center of everything. The sun, moon, and stars seemed to circle around us each day. From the perspective of someone standing on the ground, that explanation made perfect sense. It wasn't until astronomers began studying planetary motion in more detail that the truth slowly emerged. Earth is not the center of the universe. It's not even the center of our solar system. And our solar system itself is just one small region inside a galaxy containing hundreds of billions of stars. Once that realization settled in, scientists began to ask deeper questions. If our galaxy is so large, how many other galaxies are out there? The answer, it turns out, is a staggering one. Modern observation suggests that the observable universe contains hundreds of billions of galaxies. Each galaxy may contain hundreds of billions of stars. That means the total number of stars in the observable universe could easily exceed the number of grains of sand on all the beaches of Earth. And among those countless stars and galaxies, black holes appear to be surprisingly common. Some are relatively small, formed when massive stars collapse at the end of their lives. Others are much larger, sitting quietly at the centers of galaxies and influencing the motion of billions of surrounding stars. A giant horizon can feel counterintuitive in another way. Near a small stellar black hole, tidal forces can become severe before the horizon. Near a sufficiently massive supermassive black hole, the horizon is so broad that the local stretching at the boundary can be gentler, even though escape is still impossible once the boundary is crossed. But every once in a while, astronomers discover something that pushes the limits of what they expected to find. Objects that seem almost too large, almost too energetic. TON 618 is one of those discoveries. It exists at a distance of more than 10 billion light-years from Earth. That means the light we observe from it tonight actually began its journey across space when the universe was far younger than it is today. Back then, galaxies were still forming. Stars were still being assembled from clouds of gas. And somehow, in that early cosmic environment, a black hole began growing into one of the largest objects of its kind that we've ever measured. But to appreciate just how extraordinary that growth is, we need to think carefully about scale once again, because black holes behave differently from most objects we encounter in everyday life. If you double the mass of a rock, its size does not double in any dramatic way. If you double the mass of a planet, its diameter may grow slightly but not enormously. Black holes follow a much more direct relationship between mass and size. As their mass increases, the radius of their event horizon increases in a predictable way. In other words, a heavier black hole is also physically larger. That means when we say TON 618 contains tens of billions of solar masses, we're not just talking about weight. We're also talking about an event horizon that stretches across a vast region of space. A boundary where gravity becomes so strong that even light cannot escape. This boundary defines the true size of a black hole, and in the case of TON 618, that size becomes almost difficult to comprehend. Imagine drawing a circle around an object where crossing that circle means there is no possible path back out again. No rocket could escape. No beam of light could return. Everything that crosses that boundary becomes permanently trapped. For a small stellar black hole, that circle might be only a few dozen kilometers across. For the black hole at the center of our galaxy, it spans tens of millions of kilometers. For TON 618, however, the circle grows to a scale that begins to compete with the dimensions of entire planetary systems. Trying to picture something like that can feel almost surreal. Our solar system itself is already huge. The orbit of Earth around the Sun covers nearly 1 billion kilometers each year. Even the orbit of Neptune, the outermost major planet, lies billions of kilometers from the Sun. And yet, TON 618's event horizon would stretch across a region large enough to swallow a significant portion of that space. We'll explore those comparisons carefully as we move forward because they help translate abstract numbers into something more tangible. But the night sky gives us another clue about scale that's worth considering. Every point of light we see represents a moment in the past. Because light takes time to travel, looking deeper into space also means looking further back in time. The moon appears as it was 1 second ago. The growth problem is part of what makes TON 618 scientifically interesting. A black hole this massive, seen as a distant quasar, asks how early seed black holes, gas-rich galaxies, accretion limits, and mergers work together in the young universe. The Sun appears as it was 8 minutes ago. The nearest stars appear as they were years ago. Distant galaxies appear as they were millions or billions of years ago. TON 618 belongs to this distant past. When its light began traveling toward Earth, our planet was already billions of years old, but human civilization had not yet begun. In fact, complex life on land was still evolving. Dinosaurs had long since disappeared, and mammals were gradually spreading across the continents. Over the billions of years that followed, life on Earth changed dramatically. Ice ages came and went. Eventually, humans began looking up at the sky and wondering what those distant lights might be. Now, with modern telescopes and careful analysis, we can detect objects like TON 618, even though they exist unimaginably far away. That ability to measure and understand such distant things is one of the most remarkable achievements of science, but it also leads us back to the question that quietly sits at the center of tonight's exploration. If TON 618 contains tens of billions of solar masses, if it powers one of the brightest quasars in the universe, if it sits billions of light years away in a young galaxy, then just how large must its event horizon actually be? When people first hear the name TON 618, it doesn't immediately sound like anything familiar. It doesn't have a poetic name like Andromeda or Orion, or even something descriptive like the Crab Nebula. Instead, it sounds a little more like a catalog number. And that's exactly what it is. TON 618 is the name given to an object listed in a catalog of astronomical observations. The TON part comes from the Tonantzintla Observatory in Mexico, where astronomers compiled a catalog of unusual blue stellar objects many decades ago. These objects stood out because they appeared extremely bright and energetic when viewed through telescopes. At the time, no one knew that some of these strange points of light would later turn out to be among the most powerful objects in the entire universe. TON 618 was simply one entry in that catalog. Just a small, distant point of light on photographic plates. But as telescopes improved and astronomers began studying it more carefully, something remarkable became clear. TON 618 wasn't a star at all. It was something far stranger. To understand what TON 618 really is, we need to step into a category of objects known as quasars. A quasar is one of the brightest things the universe can produce. In fact, a single quasar can shine more brightly than an entire galaxy containing. That might sound almost impossible at first. After all, galaxies are enormous collections of stars, gas, dust, and dark matter. The idea that a single object could outshine an entire galaxy seems almost absurd. And yet, quasars do exactly that. The reason is that the light we see from a quasar is not coming from a star. Instead, it comes from the environment surrounding a supermassive black hole. Now, black holes themselves don't emit light. They are called black holes precisely because they trap light rather than releasing it. But the material around a black hole can become extremely bright. Gas, dust, and other matter falling toward a black hole rarely plunge straight in. Instead, they form a rotating disk around it. This structure is called an accretion disk. You can imagine it somewhat like water spiraling down a drain, except on a vastly larger scale. As matter spirals inward, gravity squeezes it tightly and forces it to move faster and faster. Friction between particles heats the material to extraordinary temperatures, amounts of radiation across many wavelengths of light. That glowing disk becomes visible across incredible distances. And when a black hole is actively feeding on large amounts of matter, the light from the surrounding disk can become so powerful that we see it as a quasar. TON 618 is one of those quasars. But it is not just any quasar. It is among the most luminous quasars ever observed. From Earth, the object appears as a faint point of light. Through a telescope, it doesn't look especially dramatic. But that faint dot represents something extraordinary. The light from TON 618 has traveled more than 10 billion years to reach us. That means when the light we see tonight left its source, the universe itself was much younger. Galaxies were still evolving. Stars were forming rapidly across the cosmos. The large-scale structures we see today were only beginning to take shape. Somewhere inside one of those distant galaxies, a black hole was growing at an astonishing rate. And that black hole is the engine powering the quasar we now call TON 618. When astronomers analyzed the light coming from this object, they noticed something unusual about the gas surrounding it. The gas was moving extremely fast. In fact, it was moving so quickly that the only reasonable explanation was the presence of an incredibly massive black hole pulling on it. Using a technique called spectral analysis, scientists studied the light from the quasar in great detail. When gas moves rapidly, the light it emits becomes stretched or compressed in measurable ways. By analyzing those changes, astronomers can estimate how fast the gas is orbiting the central object. And when they calculated those speeds, they arrived at a truly astonishing conclusion. The black hole at the center of TON 618 contains tens of billions of times the mass of our Sun. Current estimates place it at roughly 66 billion solar masses. That number alone places it among the most massive black holes ever measured. To put that into context, let's briefly revisit the black hole at the center of our own galaxy. Sagittarius. A star contains about 4 million solar masses. That already sounds incredibly large, yet TON 618 outweighs it by more than 16,000 times. Another famous supermassive black hole sits in the center of the giant galaxy Messier 87. This black hole, which was photographed by the Event Horizon Telescope in 2019, contains around 6.5 billion solar masses. That was once considered an extraordinary example of a massive black hole. But TON 618 is roughly 10 times more massive than that. Numbers like these begin to stretch our imagination in unusual ways. They're so large that they stop feeling meaningful. That's why astronomers often try to translate these values into physical size. Because the mass of a black hole determines the size of its event horizon. The event horizon is the boundary around a black hole where escape becomes impossible. If you cross that boundary, gravity would become so overwhelming that no amount of energy could carry you back out again. Even light cannot escape. For smaller black holes, this boundary can be surprisingly small. A stellar black hole containing 10 times the mass of the Sun might have an event horizon only about 60 kilometers across. That's smaller than many cities on Earth. Yet, the gravitational pull at that boundary would still be overwhelming. As the mass of a black hole increases, the event horizon grows proportionally. Double the mass and the radius doubles. Increase the mass by 1,000 times and the radius increases by 1,000 times as well. This simple relationship makes it possible to estimate the size of extremely massive black holes like the one in TON 618. And when astronomers run those calculations, the results are astonishing. The event horizon of TON 618 is estimated to span hundreds of billions of kilometers. To give that number some perspective, consider the orbit of Neptune, the outermost major planet in our solar system. Neptune travels around the Sun at an average distance of about 4.5 billion. That's already a vast distance. Yet, TON 618's event horizon is so enormous that it could easily swallow the entire region inside Neptune's orbit many times over. If the Sun were somehow replaced by this black hole, much of our solar system would lie well inside the point of no return. But TON 618's influence doesn't stop at its event horizon. Far beyond that boundary lies a vast region dominated by its gravity. Matter in this region can form enormous accretion disks, stretching across distances comparable to entire planetary jets of energy, can also erupt from the regions around the black hole, blasting radiation into intergalactic space. These energetic processes are what make quasars visible from such incredible distances. Without the glowing accretion disks surrounding TON 618, we might never have known it existed at all. The black hole itself remains invisible. What we see is the chaotic glowing environment surrounding it. And even that environment lies billions of light years away. At such distances, individual details become impossible to observe directly. Instead, astronomers rely on careful measurements of light and motion to piece together what's happening. It's a bit like listening to distant thunder and using the sound to estimate the size of the storm. You can't see every detail of the clouds, but you can still learn a surprising amount about what's happening inside them. TON 618 represents one of the most extreme examples of this kind of cosmic detective work. A faint point of light in the night sky turned out to be powered by a black hole so massive that it challenges our understanding of how such objects grow. And that raises an interesting question. How does something like this become so large? Black holes usually grow in two main ways. They can swallow nearby gas and dust, gradually adding more mass over time. Or they can merge with other black holes when galaxies collide. Over billions of years, these processes can create very large black holes at the centers of galaxies. But reaching tens of billions of solar masses is still difficult to explain. TON 618 suggests that in the early universe, some black holes may have grown much faster than we once believed possible. Perhaps they formed from unusually massive seeds. Perhaps they consumed enormous amounts of matter in extremely dense young galaxies. Or perhaps there are growth mechanisms we still don't fully understand. Astronomers are still investigating these possibilities today. But for the purpose of our journey tonight, the important thing to remember is this. TON 618 is not simply a black hole. It is the central engine of a powerful quasar, a cosmic furnace powered by gravity, a region of space where enormous amounts of matter spiral inward, heating to incredible temperatures and releasing light that travels across billions of years of cosmic history. And at the center of all that activity lies a gravitational boundary so vast that its true size is almost impossible to imagine at first. Try picturing something very simple for a moment. Imagine you are standing beside a familiar object, something you see often in everyday life, perhaps a house or a car parked along a quiet street. These are objects with sizes our minds understand easily. A car might be 4 or 5 EM long. A house might stretch 10 or 15 meters across. Even larger buildings, schools, offices, stadiums still fall within a scale that feels manageable. Your brain has spent your entire life learning how to interpret sizes like these. If someone tells you that a building is twice as large as another building, you can picture that without much effort. If someone describes a mountain as being 3 times taller than another mountain, the idea still makes sense. The numbers remain connected to real experiences, but this comfortable sense of scale begins to weaken as soon as we start looking upward into space. Earlier, we mentioned that TON 618 contains around 66 billion times That number alone is already difficult to process. Not because it is mathematically complicated, but because our intuition simply isn't built for numbers that large. And the moment we try to convert that mass into physical size, the difficulty becomes even more noticeable. Human intuition works best when it can compare things that belong to the same general category. For example, we understand the difference between a small lake and a large lake, or between a small town and a large city. Even when the difference is dramatic, the comparison still feels reasonable. Cosmic objects don't always behave that way. When black holes grow larger, their sizes increase in a very straightforward. The relationship between mass and radius is almost perfectly proportional. This means that if one black hole is 10 times more massive than another, its event horizon will also be 10 times larger. That rule sounds simple enough, but when we apply it to something like TON 618, the consequences become extraordinary. Let's begin with a smaller example to build some intuition slowly. Suppose we take a black hole with the same mass as our Sun. If the Sun was somehow compressed into a black hole, the event horizon would only be about 3 kilometers across. That means all the mass of the Sun, over 300,000 times the mass of Earth, would be squeezed into a sphere about the size of a small town. That might already sound surprising. The Sun is enormous. Its diameter stretches roughly 1.4 million kilometers across. Yet, as a black hole, it would shrink down to a sphere barely a few kilometers wide. Now, imagine a black hole 10 times the mass of the Sun. According to the same rule, its event horizon would grow to about 30 kilometers, still small by everyday standards. If you placed it somewhere on Earth, it would fit comfortably inside a large metropolitan area. But stellar black holes are only the smallest members of the black hole family. As astronomers began studying the centers of galaxies, they discovered something far more impressive. At the heart of many galaxies lies a supermassive black hole containing millions or even billions of solar masses. Our own galaxy provides a useful example: Sagittarius. A star, the black hole at the center of the Milky Way, contains about 4 million times the mass of the Sun. When we apply the same proportional rule, its event horizon expands to roughly 24 million kilometers across. That distance is already enormous. For comparison, the diameter of the Sun is about 1.4 million kilometers. This means the event horizon of Sagittarius, a star, is more than 17 times wider than the Sun itself. If it replaced the Sun in our solar system, the boundary where escape becomes impossible would extend nearly halfway to the orbit of Mercury. Already, the numbers are beginning to stretch our imagination. But TON 618 sits in an entirely different category. Instead of millions of solar masses, it contains tens of billions. And because black hole size scales directly with mass, its event horizon expands accordingly. Astronomers estimate that the event horizon of TON 618 has a radius of roughly 195 billion kilometers. The diameter, stretching from one side of the event horizon to the other, would be nearly 390 billion kilometers. These numbers are so large that they almost stop feeling meaningful unless we compare them to something familiar. One useful comparison involves our own solar. The orbit of Mercury lies about 58 million kilometers from the Sun. Venus travels at around 108 million kilometers. Earth orbits at about 150 million kilometers. Even the orbit of Neptune, the outermost major planet, lies roughly 4.5 billion kilometers from the Sun. When we place TON 618's event horizon beside those distances, something remarkable appears. The event horizon alone would extend far beyond the orbit of Neptune. In fact, it would reach several times farther than the outer planets. Imagine replacing the Sun with TON 618. Mercury, Venus, Earth, and Mars would not simply orbit close to the black hole. They would already lie deep the region where escape is impossible. The same would be true for Jupiter and Saturn. Even Neptune, which feels incredibly distant from the Sun, would be swallowed by the event horizon. Only the most distant icy objects of the outer solar system might remain outside that boundary. For many people, this is the moment when intuition begins to fail. The solar system already feels enormous to us. Space probes launched from Earth can take many years to reach the outer planets. The Voyager spacecraft, which left Earth in the 1970s, have been traveling for nearly half a century and are only now reaching the outer edge of the Sun's influence. Yet, TON 618's event horizon alone would cover a region larger than that entire planetary neighborhood. And that is just the boundary where escape becomes. The gravitational influence of the black hole extends far beyond that point. Matter orbiting outside the event horizon can still move in stable paths, forming enormous disks of gas and dust. These disks can span distances far greater than the event horizon itself. In the case of powerful quasars like TON 618, the accretion disk becomes one of the brightest structures in the universe. Gas spiraling toward the black hole heats up dramatically as it loses energy and moves inward. Temperatures climb to millions of degrees, producing radiation across the electromagnetic spectrum. The result is a luminous beacon visible from billions of light years away. All of that activity occurs in a region dominated by the gravity of the central, and the larger the black hole becomes, the larger that surrounding environment can grow. Another way to approach the scale of TON 618 is to compare it with other famous black holes astronomers have studied. In 2019, scientists captured the first image of a black hole shadow using the Event Horizon Telescope. The object in that image was the black hole at the center of the galaxy Messier 87. That black hole contains about 6.5 billion solar masses. At the time, it was considered one of the largest black holes ever measured. Yet TON 618 is roughly 10 times more massive than that. If you could somehow place both objects side by side, the event horizon of TON 618 would dwarf the one in Messier 87. But there is something even more interesting about extremely large black holes. Their event horizons are not only larger, they're also gentler in a certain sense. Near small black holes, the difference in gravity between your head and your feet would be enormous. This difference, called tidal force, would stretch objects dramatically as they approach the event horizon. The effect is sometimes described as spaghettification. For stellar black holes, this stretching would occur long before you reach the event horizon. But for ultramassive black holes like TON 618, the event horizon lies so far from the central singularity that tidal forces near the boundary are much weaker. In theory, an object crossing the event horizon of an ultramassive black hole might not notice anything unusual at that exact moment. There would be no visible surface, no sudden impact, just a quiet transition into a region where escape becomes impossible. From the outside, however, the object would appear to slow down and fade away as it approached the event horizon. The light it emitted would become stretched and dimmer, eventually disappearing entirely. This strange behavior comes from the way gravity affects time and light near extremely massive objects. It's one of the many reasons black holes remain such fascinating subjects of study. TON 618 takes all of these ideas and pushes them toward the extreme limits of what we currently observe in the universe. Its enormous mass produces a gravitational boundary larger than entire planetary systems. Its accretion disk releases enough energy to outshine the galaxy that hosts it, and its light has traveled across more than 10 billion years of cosmic history to reach our telescopes. Yet, despite all of this scale, when astronomers look at TON 618 through a telescope, it still appears as a tiny point of light, a single faint speck in the sky. This contrast between appearance and reality is one of the most remarkable things about astronomy. The universe hides its larger structures behind distances so vast that they shrink down to almost nothing from our perspective. But with careful measurement and patient observation, scientists can slowly reveal what those distant specks truly represent. And once we start translating the numbers into familiar comparisons, solar systems, planetary orbits, and distances measured in billions of kilometers, the scale begins to come into focus. TON 618 is not just another large black hole. It represents a level of cosmic growth that challenges our understanding of how such objects form and evolve. At first glance, it might seem impossible to measure something that cannot be seen. If an object does not emit light, does not reflect light, and sits billions of light years away, the challenge begins to sound almost hopeless. Our everyday experience with measuring things usually depends on being able to see them clearly. You can measure the length of a table with a ruler, the height of a building with surveying tools, or the distance to a nearby hill with a laser rangefinder. All of those methods rely on one basic principle. You can observe the object directly. Black holes remove that possibility entirely. By their very nature, black holes trap light. Any light that crosses the event horizon cannot escape again. That means the defining boundary of a black hole, the event horizon itself, remains invisible to any telescope. So, the question naturally arises, how do astronomers measure something that cannot be seen at all? The answer is surprisingly clever. Instead of trying to observe the black hole directly, scientists study everything around it. The space near a black hole is rarely empty. Gas, dust, and sometimes even entire stars can orbit nearby. These objects move under the influence of gravity, and their motion can reveal a great deal about the invisible mass at the center. Gravity, in this sense, leaves fingerprints. When an object moves through space under the influence of gravity, its speed and direction depend on how strong that gravitational pull is. By carefully measuring those motions, astronomers can work backward and calculate the mass responsible for the movement. This method has been used many times in astronomy. In fact, it was used long before black holes were ever discovered. In the 19th century, astronomers noticed that the planet Uranus was not moving exactly the way they expected. Its orbit contained small irregularities that could not be explained by the gravitational influence of the known. Instead of dismissing the problem, scientists investigated further. They realized that the strange motion might be caused by another unseen planet pulling on Uranus from farther out in the solar system. Using mathematics alone, they predicted where that hidden planet should be located. Soon afterward, telescopes were pointed toward the predicted location, and Neptune was discovered almost exactly where the calculation suggested it would be. This kind of reasoning, inferring the existence of an invisible object from its gravitational influence, became a powerful tool in astronomy. Black holes are discovered and measured using a similar approach. In the case of TON 618, astronomers did not see the black hole directly. What they observed instead was the extremely bright quasar produced by the matter swirling around it. As gas spirals toward the black hole, it forms the accretion disk we discussed earlier. This disk becomes incredibly hot, emitting enormous amounts of radiation across the electromagnetic spectrum. Telescopes can capture this radiation and spread it into a spectrum separating the different wavelengths of light, much like a prism separates sunlight into a rainbow. Inside that spectrum, astronomers look for specific patterns called emission lines. These lines come from atoms in the gas surrounding the black hole. When atoms absorb or release energy, they produce light at particular wavelengths. Hydrogen, helium, carbon, and many other elements each have their own recognizable signatures. But there is an important detail hidden within those lines. If the gas emitting the light is moving rapidly, the wavelength shifts slightly. This effect is called the Doppler shift. You might already be familiar with it when an ambulance passes by with its siren on. The pitch of the sound changes as it moves toward you and then away from you. The sound waves are compressed as the ambulance approaches and stretched as it moves away. Light behaves in a similar way. When gas moves toward us, its light shifts slightly toward shorter wavelengths, appearing bluer. When it moves away, the light stretches toward longer wavelengths, appearing redder. By measuring these tiny shifts in the emission lines, astronomers can determine how fast the gas is moving. And near a massive black hole, the gas can move incredibly fast. In the case of TON 618, the gas within the quasar's broad line region, an area close to the black hole, was observed moving at thousands of kilometers per second. Such enormous speeds immediately suggest the presence of a powerful gravitational force. But astronomers don't stop there. Once the speed of the gas is known, the next step is to estimate how far that gas is from the black hole. This distance is more difficult to determine directly, but scientists use several clever techniques. One of them involves observing how the brightness of the quasar changes over time. Quasars are not perfectly steady sources of light. The brightness of the accretion disk can fluctuate as gas falls inward and energy is released. These fluctuations propagate outward through the surrounding gas clouds. By measuring the time delay between changes in the central brightness and changes in the emission lines produced by the surrounding gas, astronomers can estimate the distance between those regions. This method is called reverberation mapping. It works a bit like shouting inside a large canyon and listening for the echo. The delay between the shout and the echo reveals how far away the canyon walls are. In a similar way, the delay between changes in quasar brightness and changes in emission lines reveals how far the orbiting gas lies from the central black hole. Once both the speed of the gas and its distance from the center are known, astronomers can apply the laws of gravity to estimate the mass of the object causing that motion. The calculation is similar to the one used to determine the mass of the Sun by studying the motion of planets. Planets orbit the Sun because of its gravitational pull. The faster a planet moves, or the closer it is to the Sun, the stronger that gravitational force must be. Gas orbiting near a black hole follows the same basic rules. For TON 618, these measurements revealed the gas was moving so quickly and at distances so large that the mass required to produce that motion had to be tens of billions of times the mass of our Sun. No ordinary object could produce such an effect. Only an ultramassive black hole could explain the observations. Once the mass is known, determining the size of the event horizon becomes relatively straightforward. black holes obey a simple relationship known as the Schwarzschild radius. This radius defines the size of the event horizon for a non-rotating black. The formula itself is elegant. For every solar mass contained within a black hole, the radius of the event horizon increases by about 3 kilometers. This means a black hole with the mass of our Sun would have a radius of about 3. A black hole with 10 solar masses would have a radius of about 30 kilometers. A black hole with 1 million solar masses would have a radius of roughly 3 million kilometers. The scaling continues smoothly as the mass grows larger. When we apply this relationship to Ton, with its estimated 66 billion solar masses, the resulting event horizon becomes enormous. The radius reaches roughly 195 billion kilometers. That distance stretches far beyond the orbit of Neptune in our solar system. Yet, even this calculation represents only the boundary where escape becomes the surrounding region dominated by the black hole's gravity extends much farther. Within that region, gas forms enormous rotating structures and powerful jets of energy may erupt from the poles of the accretion disk. These jets can extend across distances larger than entire galaxies. All of this activity provides clues that astronomers can observe and analyze, even though the black hole itself remains invisible. Its presence shapes everything nearby. This idea, studying invisible objects through their influence, is one of the most powerful methods in modern astronomy. It allows scientists to explore parts of the universe that cannot be observed. Dark matter, for example, is detected through its gravitational effects on galaxies. Exoplanets are often discovered by observing the tiny wobbles they cause in the stars they orbit. Black holes follow the same pattern. We may never see the event horizon directly for objects as distant as TON 618, but we can still measure the mass and behavior of the unseen object through the motion of the matter around it. In a way, the black hole reveals itself through the disturbances it creates. Gas accelerates, light shifts, energy radiates outward across billions of light years, and by carefully studying those signals, astronomers slowly assemble a picture of the hidden giant at the center. Extreme examples of this process. From a faint speck of light in a distant galaxy, scientists have inferred the presence of a black hole so massive that its event horizon alone would dwarf our entire planetary system. Yet, the story of how this object was first identified begins much earlier, long before its true size was understood. Decades ago, when astronomers first noticed this unusual point of light in the sky, they had no idea they were looking at one of the most massive black holes known. Long before astronomers understood what TON 618 really was, it appeared as something far less dramatic. To the observers who first recorded it, the object looked like a faint blue point of light on a photographic plate. It did not immediately announce itself as a giant black hole or a powerful. Instead, it blended quietly among many other distant objects scattered across. The story begins in the middle of the 20th century, during a period when astronomy was changing rapidly. For centuries, astronomers had relied on visual observation through telescopes. They would look through the eyepiece, carefully sketch what they saw, and record the positions of stars and planets. But by the early 1900s, photographic technology had transformed how the sky was studied. Instead of relying solely on human eyesight, astronomers could now capture large areas of the sky on photographic plates. These glass plates were coated with light-sensitive chemicals that reacted when exposed to starlight through a telescope. After the exposure, the plates were developed in a dark room, revealing thousands of tiny points of light. Each of those points represented a distant object somewhere in the stars within our galaxy. Clusters of stars, nebulae, galaxies far beyond the Milky Way, and occasionally something unusual. During the 1950s and 1960s, astronomers began paying close attention to certain objects that appeared particularly blue on these plates. Blue light in astronomy often signals extremely hot or energetic sources. Young stars, for example, can shine with a bluish color because their surfaces are very hot. But some of the blue objects cataloged during this time behaved differently from ordinary stars. They appeared star-like in telescopes, meaning they looked like small points rather than extended structures like galaxies. Yet their light carried strange signatures when studied in detail. One catalog that recorded many of these mysterious objects was compiled at the Tonantzintla Observatory in Mexico. Astronomers there were conducting a survey of blue stellar objects, points of light that appeared unusually blue compared to the surrounding stars. Each object in the catalog received a simple label, TON, followed by a number. TON 618 was one of those entries. At the time, it did not seem particularly special compared to many others. It was simply one more blue object recorded in the survey. But astronomy was entering a new era. As spectrographs improved, scientists began studying the light from distant objects in greater detail. A spectrograph spreads light into its component wavelengths, allowing astronomers to examine the unique patterns produced by different elements. When the spectrum of TON 618 was eventually analyzed, the results were puzzling. Instead of the familiar pattern seen in ordinary stars, the light from this object showed broad emission lines, bright features produced by extremely energetic gas. Even more surprising was how wide those lines appeared. Broad emission lines indicate that the gas producing them is moving at extremely high speeds. The faster the gas moves, the more its light becomes spread out across different wavelengths. For TON 618, the speeds suggested by those lines were enormous. Gas clouds appear to be moving thousands of kilometers per second. Nothing in an ordinary star could produce such motion. Around the same time, astronomers were beginning to understand a new class of cosmic objects known as quasars. The term quasar originally stood for quasi-stellar radio source. Early radio telescopes had detected powerful radio emissions coming from objects that looked like stars in optical telescopes. At first, these discoveries confused scientists. How could something that looked like a star produce so much radio energy? The mystery began to unravel when astronomers studied the spectra of these objects and realized that they were not stars at all. They were incredibly distant galaxies whose central regions were producing enormous amounts of energy. The energy source behind these quasars turned out to be supermassive black holes feeding on surrounding matter. Once this idea became widely accepted, astronomers began re-examining many of the strange blue objects that had been catalogued earlier. TON 618 quickly attracted attention. Its spectrum showed the characteristic signs of a quasar, including extremely bright emission lines produced by hot gas near a powerful energy source. But there was another important clue hidden in the spectrum. The wavelengths of the light were shifted dramatically toward the red end of the spectrum. This effect, known as redshift, occurs because the universe is expanding. As light travels across vast cosmic distances, the expansion of space stretches the wavelengths of that light, making them appear redder than they originally were. The greater the redshift, the farther the object lies from Earth. When astronomers measured the redshift of TON 618, they discovered something remarkable. The object was incredibly distant, more than 10 billion light-years away. That means the light reaching Earth today began its journey long before our solar system had completed even half of its orbit around the Milky Way. In other words, the light we see now left TON 618 when the universe itself was much younger. At such enormous distances, an object must be extremely luminous to remain visible, and TON 618 was indeed extraordinarily. When astronomers calculated its luminosity, the total energy it emits, they realized that it was shining with the power of hundreds of trillions of suns. No single star could produce that much. The only explanation consistent with the observations was the presence of a massive black hole surrounded by a rapidly feeding accretion disk. Gas spiraling inward would heat up to millions of degrees, releasing tremendous amounts of radiation. This radiation would travel across billions of light-years, eventually reaching telescopes on Earth. But the brightness of the quasar was only the beginning. As measurements improved, scientists began estimating the mass of the black hole responsible for this incredible energy. Using the techniques we discussed earlier, studying the motion of gas in the broadline region and applying the laws of gravity, astronomers arrived at a stunning: the central black hole must contain tens of billions of solar masses. That estimate placed TON 618 among the most massive black holes ever discovered. And yet, despite its enormous scale, it remains invisible. Even the most powerful telescopes cannot resolve the structure of the black hole itself. From Earth, the entire system still appears as a single distant point but that faint point represents one of the most extreme environments in the gas racing at incredible speeds, temperatures rising to millions of degrees, radiation powerful enough to outshine the galaxy that hosts it. And at the center of it all lies an event horizon so large that it would swallow our solar system many times over. The discovery of TON 618 illustrates something fascinating about astronomy. Sometimes the most extraordinary objects begin as quiet entries in a catalog, a small mark on a photographic plate, a number assigned during a survey. Only later, through careful measurement and patient analysis, does the true nature of the object reveal itself. In this case, a faint blue point of light turned out to be the visible signature of one of the largest black holes known. Yet even now, TON 618 remains far beyond our direct reach. It sits billions of light-years away, deep in the distant universe, where the light we observe today began traveling toward us when galaxies were still forming. Despite that distance, its incredible brightness allows us to study it in surprising detail. Consider the amount of light produced by an entire galaxy for a moment. A galaxy like our own Milky Way contains each of those stars, releases energy in the form of light and heat, steadily burning nuclear fuel deep in its core. Some stars, small and faint, others are large and bright, radiating thousands or even millions of times more energy than our sun. When all of those stars shine together, their combined glow creates the soft band of light stretching across the night sky that many people recognize as the Milky Way. From our position inside the galaxy, that glow can appear as a gentle river of starlight crossing the darkness. Yet, if you were far outside the Milky Way and looking back toward it, the galaxy would appear as a luminous spiral island in space, filled with billions upon billions of shining suns. That amount of light is almost difficult to imagine. But here is the surprising part. The quasar surrounding TON 618 can outshine an entire galaxy like that. One single region near a black hole can release more energy than the combined output of hundreds of billions of stars. When astronomers first realized this, it seemed almost unbelievable. For a long time, galaxies themselves were thought to be the largest luminous structures in the universe. Their vast collections of stars, gas clouds, and glowing nebulae seemed unmatched in brightness and scale. The idea that a single compact object could rival or exceed that brightness felt counterintuitive. And yet that is exactly what quasars do. To understand why, it helps to think about the difference between how stars generate energy and how matter behaves near a black hole. Stars shine because of nuclear fusion. Inside the core of a star, hydrogen atoms are squeezed together under immense pressure and temperature. These atoms fuse into helium, releasing energy in the process. That energy slowly travels outward through the layers of the star until it finally escapes as light. Fusion is extremely powerful compared with chemical reactions like burning wood or gasoline. But even fusion is not the most efficient way the universe can convert matter into energy. And so, the question that began as a question of size becomes something gentler. How big is TON 618 really? It is large enough to hold the orbits of planets inside its horizon, large enough to make the Milky Way's central black hole feel small, and luminous enough through the gas around it to send a trace of itself across billions of years. Yet from Earth it is still only a faint point of light waiting inside the dark, carrying an enormous story in a very small glow. That is the quiet scale of the universe. Not only that it can build such things, but that we can learn about them from a handful of ancient photons arriving softly in our telescopes.